Okay, we have another problem here. No, we try to consider the already try to consider the damping in a system. So we have a system here of mass m with spring and a damping coefficient c. So we were asked to find the natural frequency, and we're also asked to find the damping ratio for the system. With a given, we have a mass 10 kilograms, damping coefficient 100 kilograms per seconds, stiffness 1, 4,000 Newton per meter, stiffness 2, 200 Newton per meter, and stiffness 3 is 1,000 Newton per meter. Assume no friction acts on the rollers. Is the system overdamped, critically damped, or underdamped? So we're asked to find we are asked to find three things: the natural frequency, the damping ratio, and what else? You're asked to find if is it overdamped, underdamped, or critically damped. Okay. So what? So may una na to button. So what know if you try to look with the stiffness of the system, we have a combination here of a series and a parallel springs. So K2 and K3 are in series and K1 is in parallel. So if we try to find the equivalent stiffness of 2 and 3, that is equal to 1 over KEQ, and then we have 1 over K2 plus 1 over K3. Or eventually we have K3 plus K2 over K2 times K3. Or the K equivalent of for 2 and 3 is equal to K2 times K3 over K2 plus K3. So we just add that to our parallel. So the K equivalent of the total stiffness, we have the K1 plus K2 times K3 over K2 plus K3. That ay value ni K1 which is 4,000 Newton per meter. And then we have value for K2 that is 200 Newton per meter times 1,000 Newton per meter over 200 Newton per meter plus 1,000 Newton per meter. So our equivalent stiffness for the whole system is approximately equal to 4,167 Newton per meter. Next, what else do we need? Well, from here, we can already calculate the natural frequency, which is equal to the square root of the equivalent stiffness over the mass. So that is equal to 4,167 Newton per meter over 10 kilograms. And eventually, we'll have our natural frequency, which is equal to 20.4 radians per seconds. Next is we're asked to find the damping ratio. Sum of the damping ratio. The damping ratio is equal to the damping coefficient over 2m omega. Our damping coefficient C, we have here given 100 kilograms per seconds over 2 times the mass is 10 kilograms. And then our omega is 20.4 radians per seconds. So we'll have 100 kilograms per seconds over, we have the 2 times 10 times 20.4, which is equal to 408 kilograms per seconds. So we have our damping ratio equal to approximately equal to 0.25. Since our damping ratio is less than 1, therefore the system is underdamped. So this is in ideal condition. And then, yeah. Kumara na siya. Dali na kayo. Since we have the damping coefficient and then the stiffness, so si stiffness no, ato lang silang gikuha ng equivalent stiffness. We have a series, and then we have a parallel, and then the uban na nato tanan, we have an equivalent stiffness nga equal to 4,167. And then, kuha na to natural frequency because we're also to find the natural frequency. After getting the natural frequency, we're asked to find the damping ratio. So this is our damping ratio, the ratio of the damping coefficient over the critical damping at 2m omega. And the ratio is 0.25. And then, since the ratio is less than 1, therefore, this structure is underdamped. That's all.